Hello and welcome to the calm cosmos. This is your space to unwind, to let the day fade into the background, and if sleep comes, to drift away while the world keeps spinning gently on. Tonight's journey is about something familiar, yet often overlooked. The quiet chemistry of rain. Those drops that patter against rooftops, slide down windows and soak into the soil are carrying out delicate chemical dances that shape the air, the earth, and even life itself. Before we set out, I'd love to know where you are listening from, perhaps tucked under a blanket or halfway across the world, watching the rain fall outside your own window. If you enjoy these calming explorations, a like and a subscribe would mean a lot. And to those of you who are already part of this little community, thank you for keeping this channel alive. And don't worry, I'll do my best not to make this so fascinating that you stay up all night. But if the story of rain does hold your attention a little longer, at least you'll drift off having learned something curious along the way. So, let's begin. Have you ever wondered why rain doesn't simply fall as plain water, but carries with it scents, colours, and even secret ingredients from sky and soil alike? Rain is one of those everyday miracles that is so common we rarely pause to consider it. It falls from the sky in countless drops, nourishes fields, washes city streets, and yet beneath its simplicity is a deep reservoir of science. To speak of rain is to speak of chemistry in motion, reactions in the sky, transformations in the air, and the endless cycle that has turned over since long before humans watched the clouds. At its heart, rain is more than just water tumbling down from above. Each droplet carries with it invisible passengers, tiny particles of dust or salt that gave it birth, dissolved gases that alter its very character, and even microscopic traces of life. It is in many ways a chemical story written in falling water. The fascination lies in how those drops are formed, how they capture the essence of the atmosphere, and how they change the world when they finally meet the ground. Sometimes the chemistry of rain leaves behind a fresh earthy scent. Other times it carves stone, nourishes crops, or sweeps the air clean. For something so gentle, its influence is vast. In this exploration, we will drift from the small, the bonds that hold water molecules together, to the immense, the global cycles that carry raindrops across continents and oceans. We will listen to the quiet lessons of storms, trace the minerals and gases hidden within each droplet, and consider how rain has shaped not only the natural world, but also human history and imagination. As you settle deeper into rest, keep in mind that every rainfall is part of a timeless dialogue between the sky and the earth. It is chemistry written softly with water as its sink. And so with calm curiosity, let's step into the first chapter, the story of how a single drop of rain begins its journey, high above our heads in skies that look clear and empty. An invisible transformation is always taking place. Water, which we're used to seeing in glasses, rivers and oceans, is constantly slipping away into the air as vapour. This quiet escape is called evaporation. A puddle that shrinks on a warm afternoon, or a wet shirt that dries on the line is the same process on a smaller familiar scale. On a global stage, however, evaporation is vast. Every lake, river and ocean is steadily feeding water into the atmosphere molecule by molecule, drop by drop. What makes this possible is a property of water that is both ordinary and extraordinary. At the surface of any body of water, the molecules are in constant motion. Some of them move just fast enough to break free from their liquid neighbours and rise as gas. Temperature is the key. The warmer the surface, the more molecules gain that little bit of extra energy required to leap into the air. This is why the sea steams more on a hot day, and why tropical regions are immense sources of atmospheric moisture. Yet evaporation also happens in cool weather, just more slowly. The atmosphere is in essence a giant reservoir waiting to be stocked with water vapour. But vapour alone does not give us rain. Water molecules floating independently through the air are invisible. They can travel great distances without ever colliding in a way that produces a drop. For condensation to occur, water needs a place to begin, a seed around which to gather. This is where nucleation comes in. One of the hidden steps in the making of rain. The atmosphere is not an immaculate void. Dust lifted by winds, sea salt flung up by waves, ash from volcanoes, soot from chimneys, even grains of pollen drifting from forests. All of these act as tiny hosts. They are called cloud condensation nuclei. When vapour finds these microscopic particles, it clings to them, pulled together by the forces of attraction between molecules. Around each speck, an invisible film of water begins to form. One molecule becomes two, then a cluster, and soon what was once only air and dust is transformed into a droplet in the making. It may sound odd, but without impurities, rain would struggle to exist. Pure dust-free air resists condensation. In laboratory conditions, scientists can create what is called supercooled water vapour, which refuses to condense unless something nudges it. Nature provides the nudge in the form of these ubiquitous particles. What we might normally think of as dirt or pollution becomes in the skies the scaffolding of clouds. Yet forming a droplet is not guaranteed simply because vapour meets dust. The environment has to strike a delicate balance between temperature and pressure. At higher altitudes, the air is colder, and this cooling allows vapour to condense more readily. This is why towering clouds gather as warm, moist air rises and expands. But the pressure also plays a part. Lower pressure higher in the atmosphere allows water molecules to stick together instead of being ripped apart by constant collisions. In this sense, the birth of a raindrop is an exercise in balance. Too warm and molecules will scatter, too cold and they may freeze into crystals, just right, and the liquid drop emerges. Imagine for a moment each droplet as a tiny alchemist in the sky. Vapour, which is light, fleeting and almost ethereal, is coaxed into a new form. Around invisible grains of dust, it spins a delicate skin of liquid, transforming the unseen into something tangible. Millions upon millions of these little alchemists work at once, weaving together the fabric of a cloud. A cloud is not, as it might seem from below, a billowing lump of cotton. It is more like a vast suspension, each droplet impossibly small, often less than the width of a human hair. They hang because air currents hold them aloft, kept in balance between gravity pulling down and rising air pushing upward. Within that suspension, droplets jostle, merge, and sometimes evaporate back into vapour, only to condense again moments later. It is a restless, shifting community, always in flux. The journey from vapour to liquid is the first great act of rain chemistry. It links the oceans to the skies and sets the stage for everything that follows. Even before a single drop falls to Earth, the process has already involved countless interactions of physics and chemistry, molecules escaping heat, finding particles, aligning in clusters, and obeying the delicate rules of temperature and pressure. To stand beneath a cloud is to be in the presence of this invisible work. A soft grey ceiling overhead is in reality billions of droplets born from vapour, each one a minuscule success in the improbable act of condensation. The sky may look heavy and simple, but hidden within it is a tapestry of chemistry fine enough to escape the naked eye, yet powerful enough to change the landscape below. It is almost poetic to think that something as mundane as a dusty particle, a fleck of salt, or a wandering grain of pollen is the midwife to rain. Without them, the air could carry endless vapour, and the sky would remain empty. But with them, water finds its anchor, and the transformation begins. The chemistry is quiet, almost secretive, yet its results are familiar to every living being. From the simple puddle outside to the mighty thunderstorm overhead, all of it begins in this silent shift where vapour gives up its freedom and becomes liquid once more. If you were to ask a child to draw a raindrop, the chances are high that you would be handed a picture of something shaped like a teardrop, pointed at the top and rounded at the bottom. It is an image that has made its way into cartoons, logos, weather icons, and even road signs. Yet nature has its own geometry, and it does not follow the instructions of our crayons. A raindrop in truth does not resemble the classic teardrop at all. Its shape is dictated by physics and chemistry working together, and the reality is far more interesting than the drawings suggest. When water hangs in the air as a droplet, one of the most important forces shaping it is surface tension. Water molecules are like a group of friends holding hands. Each molecule clings tightly to its neighbours through hydrogen bonds, an invisible attraction between the slightly positive side of one water molecule and the slightly negative side of another. At the surface, where there are fewer neighbours, this bonding pulls inward, creating a skin that tries to minimise the exposed area. Left entirely to its own devices, surface tension moulds a droplet into the most efficient shape possible, a sphere. This is why tiny droplets such as mist or the dew that beads up on a leaf are beautifully round. At those small sizes, surface tension is strong enough to overcome other forces like air resistance or gravity. Mist drifting through the air is full of miniature spheres, each no wider than a strand of hair, floating gracefully because their own internal cohesion is stronger than the pull of the earth below. But raindrops do not remain tiny forever. As droplets collide within clouds, they merge and grow. Once they reach a certain size, the battle between surface tension and outside forces begins to tilt. Gravity starts pulling more firmly on the droplet, and as it falls, the air beneath it pushes upward. Imagine holding your hand out of the window of a moving car. The air presses against your palm. A falling raindrop experiences something similar, only its delicate spherical form is more easily squashed. The result is that medium-sized raindrops about 2 millimeters across no longer look like perfect spheres. Instead, they resemble a hamburger bun with the bottom flatter than the top. Push them larger still, and the shapes become stranger. At around 4 millimeter, raindrops flatten further, and the bottom can even become indented, almost like the shape of a tiny parachute. If they grow larger than that, they often split apart mid-air into smaller droplets, because the forces pulling them down exceed what surface tension can hold together. This means that the simple teardrop, while artistically satisfying, is a myth. A raindrop never sports a neat pointy top. It is either spherical when small, bun-shaped when medium, or collapsing when large. The truth is a little less tidy, but much more fascinating. It is worth pausing to appreciate the role of hydrogen bonding here. These bonds are fleeting, lasting only a fraction of a second before they break and reform, yet together they create cohesion strong enough to shape the behaviour of whole raindrops. Without hydrogen bonds, water would behave very differently. It might not even be liquid at the temperatures we're used to. The architecture of a raindrop is in many ways the architecture of water itself. Suspended mist provides a gentle counterpoint to falling rain. In mist, the droplets are so small that gravity's pull is almost negligible compared to the resistance of the air. They hang drifting lazily, sometimes suspended for hours. Walk through mist and you're not being rained on so much as being surrounded by tiny spheres, each still held tight by surface tension. It explains why mist feels different on the skin than rain. Instead of sharp impacts, it is a soft coating, a collection of microscopic spheres meeting your face. Cloud droplets are smaller still, often just a few micrometers in diameter. To put that in perspective, you could line up more than 100 cloud droplets across the width of a single human hair. They remain afloat thanks to the gentle updrafts and turbulence within the cloud. Their weight almost irrelevant compared to the constant motion of the air. It is only when these droplets combine into larger ones that gravity begins to win, and raindrops start their descent. There is something rather humorous about how consistently we have misrepresented raindrops. Cartoons give them an elegant point at the top, almost like a fashion accessory. Weather apps decorate forecasts with neat blue teardrops. Even warning signs for slippery roads display the same fictional droplet. In reality, if one were to be brutally honest, a medium raindrop is shaped more like a squashed burger bun than a graceful tear. Perhaps not as marketable, but much closer to the truth. Understanding the architecture of a raindrop is not just a curiosity. It affects how light bends and scatters within it, which gives us rainbows. It affects how fast the drop falls, how much water reaches the ground, and even how soils absorb moisture. A perfect sphere would behave differently than a flattened oval, and the tiny shifts in geometry change the way rain interacts with the world. On the ground, this architecture even changes the sound of rain. Small spherical drops create a lighter patter. The next time you listen to rainfall, you're hearing a symphony of different shapes striking surfaces at different speeds, all orchestrated by surface tension, hydrogen bonds, and the pull of gravity. It is easy to forget that each drop overhead is a chemical and physical masterpiece, designed not by an artist's hand, but by the laws of nature. Their architecture is a compromise between cohesion and collapse, between the pull of neighbours and the tug of the earth, between invisibility and mist and drama in a storm. A raindrop may not look the way we draw it, but in its quiet architecture, it carries a story far richer than any cartoon could capture. There are few experiences more instantly recognisable than the smell of rain. Step outside after a summer shower, or breathe deeply as the first drops strike parched ground, and the air changes in a way that feels almost magical. It is fresh, earthy, and strangely comforting. Poets have celebrated it, perfumers have tried to capture it, and scientists have given it a name, petrichor. Behind that soothing fragrance lies a blend of plant oils, microbial byproducts, and even the chemistry of lightning. Each rainfall is in effect a complex perfume crafted by nature. The term petrichor was first coined in the 1960s by two Australian researchers, Isabel Baer and Richard Thomas. They wanted to describe the distinctive scent that accompanies rain on dry soil. The word itself is a fusion of Greek roots. Petra meaning stone and eor, the mythical fluid said to flow in the veins of the gods. It was a poetic choice for what is at its heart a down-to-earth bit of chemistry. Petrichor begins with plants. During long dry spells, many plants exude oils that seep into the soil and cling to rocks. These oils serve practical purposes. Some act as growth regulators for seeds, others as deterrents against competing vegetation. Left to accumulate, they sit dormant in the dust and earth, waiting for the right trigger. When rain finally falls, the impact of droplets releases these oils into the air, carrying their aroma upward in tiny bursts. The scent is subtle yet powerful, one that people across cultures instantly recognize. But petrichor is not the only contributor. Another key ingredient is a compound called geosmin. The name means earth smell, and that is exactly what it provides. Geosmin is produced by a group of soil-dwelling microbes known as actinobacteria. These microbes are ancient, abundant, and busy recyclers of organic matter. As they live and die, they release geosmin into the soil. When rain disturbs the ground, it liberates geosmin into the air, where human noses, incredibly sensitive to the compound, pick it up in even the tiniest concentrations. To put it in perspective, people can detect geosmin at levels as low as a few parts per trillion. That is like noticing a single drop of dye in an Olympic swimming pool. Geosmin provides the earthy, musty quality of rain smell. It is why freshly turned soil or a garden after watering can smell almost intoxicating. Combined with the plant oils that make up petrichor, it creates a fragrance that is at once sharp, clean, and grounding. Some describe it as nostalgic, a scent that carries memories of childhood summers, of running through fields, or of standing on a porch watching a storm arrive. Then there is the sharp, almost metallic note that sometimes accompanies thunderstorms. This comes from ozone, a molecule made of 3 oxygen atoms. Normally oxygen is content to exist in pairs, but when lightning splits these molecules apart, some recombine in trios, creating ozone. The gas is unstable and does not linger for long at ground level, but storms can draw it down from higher altitudes where it is more abundant. The result is that faint, sharp tang in the air before or during a thunderstorm, a smell that signals both energy and renewal. Taken together, petrichor, geosmin, and ozone create rain's unique aroma. Not every shower smells the same because the proportions vary. A light drizzle after a long dry spell will release more petrichor, while a thunderstorm may emphasize ozone. A gentle rain in a forest will smell different than rain striking city streets because the soils and microbes are different. Yet in each case, the chemistry works on us in profound ways. Why, though, do humans find these smells so calming? Part of the answer lies in biology. Our noses are remarkably sensitive to geosmin, far more than to many other compounds. Some researchers speculate that this sensitivity evolved because recognizing the smell of damp soil could help our ancestors locate fresh water sources. If so, then our appreciation of rain scent may be a faint echo of survival instincts. There is also psychology at play. Rainfall often comes with cooler air, softer light, and the rhythmic sound of droplets. Together with the fragrance, these cues can trigger memories and associations. Many people link the smell of rain with safety, comfort, or childhood moments of shelter. The combination of sensory input creates a soothing cocktail for the mind, lowering stress and encouraging relaxation. Interestingly, not everyone interprets the scent in exactly the same way. In perfumery, geosmin can be divisive. Some people adore its earthy character, while others find it overpowering or even unpleasant in concentrated form. Yet in the diluted natural blend produced by rainfall, it seems to strike the right chord. Perhaps the fleeting nature of rain's perfume makes it all the more precious. It is there one moment, gone the next, a reminder of the temporary beauty in ordinary events. There is even a touch of humour in how universally beloved this smell is. Humanity may disagree on countless things, from food preferences to political views, but set a rainstorm across a dry landscape and most noses perk up in unison. Few scents manage to unite us quite like the earthy signature of rain. When you take in that first deep breath after a storm, you're inhaling the combined work of plants, microbes, and lightning. It is chemistry broadcast into the air, tuned perfectly to human senses. Each whiff is a story of waiting oils, industrious bacteria, and the crackling power of thunderstorms stitched together into a fragrance that has followed our species for as long as we have walked the earth. The smell of rain is in many ways a reminder that chemistry is not always confined to laboratories or textbooks. It is present in the world around us, quietly shaping experiences we take for granted. Whether it comes as a whisper of petrichor after a dry season, a grounding wave of geosmin from the soil, or a sharp flash of ozone from a storm, the perfume of rain is one of nature's most elegant signatures, a symphony of molecules that makes the world feel both refreshed and renewed. When most people think of rain, they imagine it as pure water falling from the sky, a kind of distilled gift from the clouds. In reality, every raindrop carries with it a bit of chemistry that shapes its character. One of the most important traits is acidity, a measure captured by that familiar scale of pH. While we often think of water as neutral with a pH of 7, natural rain is not quite so balanced. It tends to be a little acidic, hovering around a pH of 5.6. And there is a very good reason for that. The atmosphere is full of carbon dioxide. As water vapour condenses into droplets, it dissolves small amounts of this gas. Once inside, the carbon dioxide reacts with the water to form carbonic acid, the same weak acid that gives sparkling water its fizz. Though the effect is gentle, it is enough to nudge the rain below neutral on the pH scale. This mild acidity is entirely natural and has been a feature of rainfall for as long as the Earth has had both an atmosphere and water. Far from being harmful, it plays a role in weathering rocks, releasing minerals into soils and sustaining natural cycles. But the balance shifts when other gases enter the picture. Industrial activity. Power plants and vehicles release sulfur dioxide and nitrogen oxides into the atmosphere. These gases, once airborne, meet with water droplets and undergo chemical reactions to form stronger acids, such as sulfuric acid and nitric acid. The rain that carries these compounds has a pH significantly lower than natural rainfall, sometimes dipping to values around 4 or even 3. This phenomenon is what we know as acid rain. Acid rain became a major environmental concern in the 20th century, but its history goes back further. During the Industrial Revolution in the 18th and 19th centuries, coal was the dominant fuel. Burning coal releases large amounts of sulfur dioxide, and in heavily industrialised cities like London and Manchester, this gas mixed freely with rain. The result was not only acid rain, but also thick, choking smog that turned the air into a soup of soot and acid droplets. Accounts from the time described blackened buildings, dying forests and rivers that could no longer support fish. Even marble statues were scarred as the acid rain reacted with calcium carbonate, eating away at delicate features and inscriptions. The stone faces of history literally dissolved under the touch of polluted rain. In forests, the problem was equally severe. Acid rain leached nutrients like calcium and magnesium from soils, depriving trees of essential elements. At the same time, it freed up aluminum ions that were toxic to roots. Entire stands of spruce and fir withered under the combined stress of poor nutrition and direct acid damage to their leaves. In lakes, fish populations collapsed as water acidity increased beyond what eggs and young fry could tolerate. The recognition of acid rain's destructive power sparked a wave of scientific investigation in the mid-10th century. Researchers in Scandinavia noticed that lakes were dying, even far from industrial centres, and they traced the cause back to airborne pollutants drifting across national borders. This discovery was both alarming and important. It meant that pollution in one country could acidify rainfall hundreds of kilometres away. Acid rain was not a local issue, it was a regional and even international one. Policies began to change in response. By the late 20th century, many nations introduced stricter controls on emissions of sulfur dioxide and nitrogen oxides. Technologies such as scrubbers in power plants helped capture sulfur before it could escape into the sky. Cleaner fuels and catalytic converters in cars reduced nitrogen emissions. The results were encouraging. In many regions, rainfall gradually became less acidic, lakes began to recover, and forests showed signs of renewal. The story of acid rain is often presented as one of environmental harm, but it is also an example of how scientific understanding can lead to effective solutions. Of course, not all rain leans toward acidity. In certain regions, particularly those rich in dust or limestone, rainfall can actually be slightly alkaline. Winds that whip across deserts lift fine particles of calcium carbonate and other alkaline minerals into the air. When rain droplets form around these dust particles, the minerals dissolve, raising the pH of the water. Instead of being acidic, the rain becomes buffered, more neutral, or even mildly basic. This alkaline rain can offset some of the natural acidity of carbon dioxide, and in agricultural areas may even contribute valuable minerals to the soil. The chemistry of rainfall, then, is never uniform. It depends on the gases in the atmosphere, the presence of dust and minerals and the local geography. A storm passing over a coal-fired industrial zone in the 19th century would produce rain chemically different from one sweeping across a modern desert plain. Even within the same storm system, rainfall can vary depending on what particles and gases droplets encounter as they form and fall. There is a touch of irony in all this. Rain, which many people instinctively associate with purity, is in fact a chemical mirror of the air it falls through. It reflects the history of each cloud's journey. Whether that includes drifting above forests releasing plant vapours, over oceans casting salt into the air, or across cities thick with human industry. The acidity or alkalinity of rain is like a signature of the atmosphere's recent past. For most of human history, people did not realize rain carried such a chemical imprint. It was simply water from the sky. Sometimes nourishing, sometimes destructive, but always taken for granted. It took centuries of observation. And finally, the tools of modern chemistry to understand that every raindrop is a little laboratory in motion. Its pH is not fixed, but dynamic, shaped by an interplay of natural gases, industrial emissions, and dust carried on the wind. The quiet lesson of rain's acidity is that something as ordinary as a shower can hold a complex record of both natural processes and human activity. Each drop is more than just water. It is a balance of carbon dioxide, minerals, and sometimes pollutants, all written into its chemistry. To watch rainfall is to witness not only weather but also the invisible dialogue between earth, sky and humanity, expressed in the language of pH. A thunderstorm is one of nature's most dramatic performances. The sky darkens, clouds tower into anvil shapes, and distant rumbles announce the arrival of lightning and rain. To the senses, it feels like a grand spectacle of light and sound. But hidden inside those bolts of electricity and sheets of falling water is chemistry of surprising importance. Thunderstorms do not simply shake the air, they also change it, forging new compounds that descend to the earth with the rain. Among the most remarkable of these products are nitrates, essential nutrients for life on the ground. To understand how this works, imagine the extraordinary power packed inside a bolt of lightning. A single flash can reach temperatures hotter than the surface of the sun, around 30,000 °C. At that heat, molecules in the atmosphere do not stand a chance. Nitrogen and oxygen, which normally prefer to remain as stable pairs of N2 and O2, are ripped apart into individual atoms. For a brief moment, the air is filled with reactive fragments that do not like being alone. Almost instantly, they crash back together, but in new combinations. Some of the nitrogen atoms join with oxygen atoms, creating nitrogen oxides, such as nitric oxide and nitrogen dioxide. These molecules in turn dissolve into raindrops, where they react further to form nitrates. Nitrates are special because they are a form of nitrogen that plants can actually use. Although the air around us is about 78% nitrogen, it is mostly locked in the form of N2, which is stubbornly unreactive. Plants cannot simply inhale nitrogen gas and use it to build proteins. They need it to be fixed, converted into compounds like ammonium or nitrate. Lightning provides one of nature's original nitrogen fixing systems, breaking apart that tough nitrogen bond with sheer electrical violence and delivering the results back to the ground in every storm. In this way, a thunderstorm doubles as a fertilizer factory. Each bolt adds to the supply of nitrates that sink into the soil with the rain. For early ecosystems, long before humans learned how to make fertilizer in factories, this process was crucial. It distributed life's essential elements across the landscape. The very proteins in our bodies and the chlorophyll in leaves trace their existence back in part to the nitrogen delivered by storms. Of course, lightning is not the only nitrogen-fixing process on Earth. Certain bacteria in soils and the roots of legumes perform the same task biologically using enzymes instead of electricity. But the role of storms is still significant. And what is more, it spreads nitrate evenly across large areas, not just around clusters of plants. Every clap of thunder is, in a sense, the sound of the atmosphere recharging the ground with one of life's indispensable ingredients. Alongside nitrates, thunderstorms also generate ozone. When lightning splits oxygen molecules, some of the fragments recombine as O3, the triatomic form we know as ozone. Normally, most ozone lives in the stratosphere high above where it protects life from ultraviolet rays. But during storms, small bursts of ozone can form at lower levels. This is what gives the air a sharp, fresh scent around storms, a tang that people often describe as metallic or electric. It is short-lived because ozone is unstable and breaks down quickly, but for a moment it adds to the unique perfume of a thunderstorm. These temporary surges of ozone and nitrates demonstrate how energetic storms are. They do not merely rearrange the weather, but actively alter the chemistry of the sky. For scientists, thunderstorms are laboratories of extreme conditions. They offer insight into how high-energy events influence air composition, and even into how similar processes might occur on other planets with lightning-rich atmospheres. Jupiter and Saturn, with their massive storm systems, could be performing the same atmospheric chemistry on a scale far beyond anything seen on Earth. Historically, humans have sensed the fertility of storms without necessarily knowing the chemistry behind them. Farmers long ago observed that crops often seemed greener and more vigorous after a series of thunderstorms. The rains not only watered the fields, but also delivered something extra, though it took centuries to discover that nitrates were the hidden gift. Ancient myths sometimes treated thunder as the voice of gods, hurling power and fertility down to the soil. While the stories were poetic, they were also rooted in an observation of real benefits. Even today, though industrial fertilizers now dominate agriculture, thunderstorms still quietly contribute to soil health. It is estimated that lightning fixes around 5 to 20 million tons of nitrogen into usable compounds each year. That may be small compared to human fertilizer production, but it's far from trivial. It ensures that natural ecosystems, forests and grasslands continue to receive nitrogen without human intervention. The idea of rain as a delivery system is worth lingering on. Each droplet falling from a storm is more than water. It is a carrier of dissolved gases and nutrients, a chemical message from sky to soil. When the droplets sink into the ground, the nitrates spread into root zones where plants absorb them to build proteins, enzymes and DNA. From there, the nitrogen enters food chains, cycling into animals and eventually back into the air when organic matter decays. The thunderstorm is a spark that keeps this grand nitrogen cycle moving. There is something almost paradoxical about the whole process. Thunderstorms often feel chaotic and destructive. Roaring winds, crashing sounds, and blinding flashes of light. Yet out of that violence comes nourishment. The same strike of lightning that frightens with its power also forges molecules that sustain life. It is a reminder that the natural world does not separate creation and destruction neatly. Often they arrive together, bound in the same flash of energy. So the next time the sky rumbles and rain pours down, it is worth remembering that there is more happening than meets the eye. Inside every storm, atoms are being torn apart and recombined. Raindrops are becoming enriched with nutrients, and the soil below is quietly preparing for a burst of growth. A thunderstorm may announce itself with sound and fury, but in its chemistry lies a softer truth. It is one of the planet's oldest gardeners, sprinkling the earth with the ingredients of life. Rain has many talents, but one of its most overlooked roles is that of a cleaner. When the clouds finally open and drops begin to fall, they do more than water the ground. Each droplet becomes a tiny janitor of the skies, sweeping up dust, soot, pollen, and even traces of pollution that were floating invisibly above us. The result is a kind of atmospheric house cleaning, which is why the world often feels fresher and clearer after a storm has passed. The process begins even before the raindrop leaves the cloud. As water vapor condenses around particles, it traps whatever was already suspended in the air. These can be bits of sea salt, smoke, volcanic ash, or industrial emissions. Scientists call this rain-out, the capture of particles during droplet formation. In essence, the drop is born, already carrying some of the atmosphere's clutter. When it finally falls, it delivers that package back to the Earth, locking the particles out of the air and into soil or water. But the real magic happens on the way down. As raindrops tumble through the sky, they collide with and absorb other particles drifting in the air. This is known as washout. Imagine billions of tiny vacuum cleaners falling from the clouds, each one sweeping up whatever it touches. Dust that was floating high above, smoke from chimneys, pollen grains that were irritating noses. All of these can be captured by falling rain and pulled to the ground. The air is literally scrubbed clean, not by machines but by gravity and chemistry working together. It is easy to notice the difference. After a heavy rain, the horizon often looks sharper, colours more vivid, and the air feels lighter to breathe. This freshness is not an illusion. With fewer particles scattering light, visibility improves dramatically. Fewer pollutants in the air mean less irritation to lungs and noses, which partly explains why stepping outside after a storm can feel invigorating. The cleansing effect of rain is especially important in cities. Urban air is thick with particles from traffic, construction, and industry. Soot from engines, microscopic bits of tyre rubber, and dust from endless building projects accumulate in the atmosphere. Rain offers a natural reset, temporarily lowering pollution levels and clearing the view. Of course, city rain can be dirtier when it lands because it gathers all those pollutants along the way. Puddles may turn grey, and runoff may carry contaminants into drains, but for a brief period the air above feels renewed. In rural areas, the cleansing is gentler, but no less important. Here, the air is often loaded with pollen, spores, and natural dust stirred by winds. Rain quiets these irritants, pressing them back into the soil where they belong. Farmers sometimes welcome rain not just for watering crops, but also for clearing the air during heavy pollen seasons. Even forests benefit as leaves washed by rain are freed of dust, allowing them to breathe more efficiently through their stomata. The chemistry behind this cleaning is fascinating. Water molecules are polar, meaning they have a slight positive charge on one end and a slight negative charge on the other. This allows them to attract and bind with many different kinds of particles and gases. Some pollutants dissolve readily in water, such as sulfur dioxide and nitrogen oxides, which means raindrops can capture them efficiently. Others, like dust grains, are simply carried along physically. Either way, the end result is the same: less clutter in the air. The scale of this operation is immense. A single rainstorm can remove millions of tons of material from the atmosphere. Scientists who measure air quality often see dramatic drops in particle concentrations following rain. It is as if nature occasionally flips a switch, sweeping the skies in one great downpour. This effect is so reliable that researchers sometimes wait for rain events to reset their instruments before measuring new pollution levels. The fresh feeling after rain is enhanced by another factor: negative ions. Falling water droplets can break apart and generate these charged particles, which some studies suggest may contribute to the sensation of clean, invigorating air. While the science on their direct health effects is still debated, there's no doubt that freshly washed air feels different to breathe, crisp in a way that dry, dusty air never does. Of course, rain's cleaning ability has its limits. In heavily polluted areas, the particles it carries down do not simply vanish. They accumulate in soils, waterways, and urban infrastructure. Acid rain in particular demonstrated how cleaning the air could sometimes shift the problem downward, harming ecosystems and corroding buildings. Rain is an excellent cleanser of skies, but it does not eliminate pollution, it redistributes it. Yet, despite these caveats, the role of rain as an atmospheric cleaner is profound. It shapes ecosystems by removing dust that might otherwise block sunlight or clog plant pores. It affects climate because particles influence how sunlight interacts with the atmosphere, and it impacts human health by reducing the fine particulate matter that contributes to respiratory issues. Every shower is in its own quiet way an act of maintenance for the planet's atmosphere. There is something poetic about this invisible housework. We see the drops splash on pavements and fields, but above us, each one has already been hard at work, scrubbing, collecting, and restoring balance to the air. The next deep breath you take after a storm is not just psychological relief, it is the taste of cleaner, clearer skies. Rain's chemistry is not always dramatic, but it is unfailingly thorough, washing the heavens so that life below can breathe a little easier. Rain has a way of transforming the sky into a canvas after a storm when the clouds begin to part and the sunlight returns. A rainbow may stretch across the horizon as if nature had decided to sign its work with a flourish of colour. It feels almost magical. But the secret of the rainbow is rooted not in mystery, but in physics and chemistry, working hand in hand within countless tiny raindrops. Each droplet acts like a prism, bending and scattering light into its constituent colours. And when millions of them shine together, they paint the air with arcs of red, orange, yellow, green, blue, indigo, and violet. The story begins with light itself. Sunlight appears white to our eyes, but in truth, it is a blend of many different wavelengths, each corresponding to a different colour. When that light encounters a change in medium from air into water, for instance, it bends, a process known as refraction. This is why a straw looks bent in a glass of water, and why your legs seem oddly shortened when you wade into a pool. In a raindrop, sunlight refracts as it enters, bending slightly as it slows down in the denser medium of water. But the bending does not stop there. Inside the droplet, the light is reflected off the inner surface, and then refracted once again as it exits back into the air. This sequence of refraction, internal reflection, and refraction again, is what turns each raindrop into a tiny projector of colour. The key is that each wavelength of light bends by a slightly different amount. Red, with its longer wavelength, refracts less sharply than violet with its shorter wavelength. The result is dispersion, the spreading out of white light into a spectrum of colours. For a rainbow to appear, geometry is crucial. The angle between the incoming sunlight, the droplet, and the observer's eye determines whether the refracted and reflected light reaches you. The most brilliant rainbows occur when the sun is low in the sky, usually in the early morning or late afternoon. The light then enters raindrops at just the right angle, about 40 sudig for red light, slightly less for violet, to send the spectrum back toward your eyes. This is why you cannot see a rainbow at noon with the sun overhead. The geometry simply does not allow it. A rainbow is not actually a fixed object hanging in the sky. It is an optical phenomenon created by countless droplets reflecting light toward you from just the right angles. Move a few steps and the rainbow you see is technically a different one, constructed by a new set of droplets at those angles. In a sense, a rainbow is personal, a colourful arc tailored to your particular vantage point. Sometimes a second rainbow appears above the first. This double rainbow is created when light reflects not once but twice inside the raindrop before emerging. With two internal reflections, the geometry changes and the secondary rainbow forms at a wider angle about 50°. Because of the extra reflection, the colours of the secondary rainbow are reversed with red on the inner edge and violet on the outer. Double rainbows are fainter because more light is lost with each reflection, but when they appear, they add an extra touch of drama to the sky. If you look closely at the inner edge of a bright rainbow, you may notice a series of faint, closely spaced bands of colour. These are called supernumerary bows. Unlike the main arc, which arises from straightforward refraction-reflection, supernumerary bows result from the wave nature of light. As light waves overlap and interfere inside the droplet, they create additional fringes, delicate pastel bands just inside the primary rainbow. Their presence reveals the dual personality of light, particle, part wave, acting in ways that only physics can fully explain. Raindrops themselves determine much of the rainbow's character. Small droplets tend to produce rainbows that are more pastel and washed out because the dispersion is less distinct. Larger droplets, by contrast, create vivid, sharply defined colours. This is why rainbows after heavy showers can appear more brilliant than those formed by mist. In fog or fine drizzle, rainbows often look pale or ghostly, sometimes called fog bows, with broad white arcs instead of bright colour. The physics of rainbows has fascinated scientists for centuries. Aristotle mused on their geometry, while medieval scholars puzzled over how colours emerge from light. In the 17th century, Isaac Newton famously used a glass prism to demonstrate that white light contains the full spectrum of colours, proving that rainbows are not painted in the sky by the heavens, but revealed through the bending of light itself. Yet, even with the science laid bare, the sight of a rainbow continues to evoke wonder. Part of the magic comes from the fact that a rainbow is fleeting. It lasts only as long as sunlight strikes droplets at the right angle. A passing cloud, a change in the position of the sun, or a shift in rainfall can make it vanish in an instant. That transience adds to its beauty, a reminder that not all spectacles are meant to linger. There is also a universal quality to the rainbow across cultures. It has been taken as a sign of peace, hope, or connection between earth and sky. Legends and myths wrapped it in meaning long before anyone spoke of refraction or dispersion. Even now, a rainbow can silence conversation as people stop to gaze upward. Science may explain the mechanics, but it does not diminish the sense of wonder. Every rainbow you see is the work of millions of raindrops, each one a lens and a mirror, each one splitting sunlight into its hidden colours. Together they weave a grand arc across the sky, a chorus of physics and chemistry made visible. The next time sunlight and rain meet at just the right moment, take a moment to watch the spectacle unfold, knowing that within each shimmering band lies a lesson in the quiet power of water and light. Every raindrop begins its life as more than just water. To condense at all, vapour needs a speck to cling to, a nucleus around which it can gather. Those seeds are usually tiny fragments drifting in the air, grains of dust, crystals of sea salt, microscopic bits of volcanic ash, or even pollen. While they may seem insignificant, these particles shape the chemistry of rain and in turn influence the world below. Each falling drop is not simply liquid from the sky, but a courier carrying minerals and elements across the surface of the planet. Consider the role of dust. Winds sweep across deserts and dry plains, lifting fine particles into the atmosphere. The Sahara Desert, for instance, is a vast supplier of airborne dust, sending plumes high into the air that travel thousands of kilometers across oceans. When raindrops form around this dust, they capture its mineral load, and when they finally fall, they deliver it to faraway ecosystems. This is not a minor contribution. Dust from the Sahara feeds soils in the Amazon rainforest, replenishing nutrients that would otherwise be lost to heavy rains and rapid plant growth. The cycle links continents with raindrops as the goat weans. Sea salt plays an equally important role. When waves break, they fling tiny droplets of seawater into the air. These droplets dry, leaving behind crystals of salt that drift upward and wait for moisture to gather. Raindrops forming on these salty seeds carry a faint briny signature. Over oceans, this process is constant, ensuring that marine air is rich with salt particles. When rain falls back into the sea, the chemistry is more or less recycled. But when sea salt-laden rain drifts inland, it can deliver sodium, chloride, and other ions to soils far from the shore. Plants and ecosystems benefit from this gentle seasoning, though too much salt, of course, can be harmful. Volcanic ash adds another ingredient to the mix. During eruptions, volcanoes release not just dramatic clouds of smoke, but also enormous amounts of fine ash and mineral-rich dust. These particles lofted into the stratosphere can remain aloft for months or even years, seeding raindrops across the globe. The minerals carried in volcanic ash are diverse, including silica, iron, calcium, and potassium. When incorporated into rain, they enrich soils, making volcanic regions some of the most fertile on Earth. Farmers living near volcanoes may dread eruptions for their danger, but also know that the ash eventually blesses the land with extraordinary fertility, a gift often delivered through rain. All of this means that raindrops are not chemically identical everywhere. Rain falling over oceans tends to be slightly salty, carrying traces of marine aerosols. Rain sweeping across deserts may hold alkaline minerals like calcium carbonate, making it less acidic than normal. In contrast, rain in areas dominated by forests may carry organic compounds from plant emissions. Each shower has its own chemical fingerprint, a reflection of the particles it encountered on its journey from vapour to liquid. The impact on soil fertility is profound. Nutrients dissolved in raindrops become part of the Earth's cycles available to plants and microbes. Nitrates from thunderstorms fertilise crops. Dust minerals support lush forests. Even trace elements such as iron delivered in Saharan dust can stimulate plankton blooms in distant OC. In this way, raindrops link ecosystems across the planet, redistributing the building blocks of life in quiet, persistent ways. It is easy to imagine each raindrop as a tiny courier travelling from sky to earth with a package of minerals tucked inside. Some may carry a pinch of desert dust, others a crystal of sea salt, others a fragment of volcanic glass. Released by the fall, these small gifts scatter into soils, rivers and oceans, feeding cycles that sustain life. Individually, the cargo seems trivial. Collectively, over billions of drops, it is a system of delivery on a planetary scale. The chemistry also affects how rain feels and smells. Sea salt rain, for instance, can have a crisp freshness that inland rains lack. Dewstrick rain can alter the pH, making it more alkaline than the mild acidity caused by carbon dioxide alone. In some regions, people notice mud rain when Sahara and dust or other particles are so abundant that raindrops fall visibly stained with soil. Cars, windows, and laundry left outside may be speckled with reddish or brown spots. Visible proof that the sky's been carrying cargo across continents. The long distance transport of minerals through rain is a reminder of how interconnected the Earth really is. A shower falling in the Amazon may owe some of its nutrients to winds in Africa. Crops in Europe may receive salts born of waves in the Atlantic. Even the clarity of a remote mountain lake can be influenced by volcanic ash deposited halfway around the world. What seems like a local rainstorm is often tied to processes that span thousands of kilometers. This mineral delivery is not always beneficial. Alongside natural dust and salt, raindrops can also carry pollutants, heavy metals, soot, or chemical residues from human activity. These too become part of the raindrop's cargo with less friendly consequences for ecosystems. Yet even here, the principle remains the same. Every droplet is a vehicle carrying more than just water, redistributing whatever the atmosphere provides. When you think of rain in this way, the sky becomes not just a reservoir of water, but also a network of couriers dispatching millions of tiny packages to the ground below. Some of those packages are filled with nutrients that feed forests and oceans. Others hold reminders of distant deserts or restless volcanoes. Together they ensure that the chemistry of the Earth remains dynamic, that no ecosystem is ever entirely cut off from the rest. Every drop that splashes onto a leaf or trickles into the soil carries a story written in dust, salt, and minerals. Raindrops are more than water. They are messengers delivering fragments of Earth back to Earth, ensuring that life continues to be nourished in places far from where those fragments began. Water has been on Earth for billions of years, and yet it never truly disappears. It only moves, changing form and place in a continuous cycle that touches every corner of the planet. This is the global water cycle, a process so familiar that it is often taken for granted, yet so profound that it sustains every living thing. At its heart lies chemistry, the shifting bonds between molecules, the dissolving of gases, the constant interplay between liquid, vapour, and ice. Rain is one of the most visible stages in this cycle, but the journey of water is vast, ancient, and endlessly repeated. The cycle begins with evaporation, driven by the sun's energy. Water molecules at the surface of oceans, rivers, and lakes gain enough energy to break free from their liquid neighbours and rise as vapour into the atmosphere. Each escaping molecule is part of a collective migration. Vast amounts of water vapour are lifted every day, especially from warm seas, and yet we hardly notice it happening. Even in colder places, evaporation ticks away slowly, powered by the sun's steady hand. Alongside evaporation, plants contribute through transpiration, releasing water vapour from their leaves as part of photosynthesis and respiration. Together, these processes feed the skies with an invisible reservoir. As this vapour rises, it cools. Molecules moving at high speeds slow down in the thinner, colder air of higher altitudes. This cooling encourages condensation, the process where vapour returns to liquid form. With the help of dust, salt, or other airborne particles, water molecules cluster into droplets. When enough droplets gather, they create clouds, those great visible symbols of the cycle in motion. To the eye, a cloud may look light and fluffy, but in truth, it holds massive amounts of water suspended above the ground. Eventually the balance tips. Droplets collide and merge, growing heavy enough that rising air currents can no longer support them. Gravity takes hold and precipitation begins. This might fall as rain or, depending on temperature, as snow, sleet, or hail. Each drop or crystal is a small delivery carrying water back to the Earth's surface in a ceaseless exchange. What makes this cycle remarkable is that it is not just happening now, but has been happening for billions of years. Many of the molecules of water in a glass or in the raindrops sliding down a window have been circulating since the earliest days of the planet. Some may have fallen as rain on ancient forests when dinosaurs walked the Earth. Others may have frozen into glaciers, locked away for millennia before melting and rejoining the flow. A single molecule might have spent centuries drifting in the ocean before evaporating again. A traveller on a grand looping journey. This recycling is so complete that no new water is truly made or lost on Earth. The water we use, drink, or wash with today is the same water that once coursed through rivers in prehistoric times, the same that filled primeval seas, the same that formed ice in ancient polar caps. When rain falls, it is not the birth of new water, but the return of old companions, endlessly reshuffled. It is little wonder that people often describe rain as refreshing. Each drop is both present and ancient, a reminder of continuity across unimaginable spans of time. Rainfall links the parts of the cycle together. From the ocean, water vapour rises, condenses, and returns as rain, replenishing rivers and lakes. From glaciers, melting ice feeds streams that join those rivers, their waters eventually returning to the sea. Groundwater too plays its role, absorbing rain that seeps into soils and aquifers only to resurface through springs or wells. Nothing is wasted. Every pathway leads back into the cycle, even if the journey takes thousands of years. Chemistry shapes each stage. The polarity of water molecules with their slight positive and negative charges allows them to bond and unbond with ease. Moving between states with small changes in energy, the dissolving of carbon dioxide in rain gives it a mild acidity, helping it weather rocks and release minerals into rivers. The freezing and melting of ice depend on the hydrogen bonds that form crystalline lattices, making ice less dense than liquid water, a property unique in nature. Without these quirks of chemistry, the water cycle would look very different. The cycle also acts as the Earth's climate regulator. As water evaporates, it carries heat away, cooling surfaces. When it condenses into clouds and rain, it releases that stored heat into the atmosphere, driving weather systems and distributing energy across the globe. Rain then is not just a local event, but part of a planetary system of balance, transporting heat as well as water from one region to another. There is a poetic truth in recognizing that every raindrop carries an ancient memory. When it splashes onto your hand, you're touching water that may once have rolled off the back of a mammoth, trickled through a canyon in its youth, or lain frozen deep inside a glacier for tens of thousands of years. Some of it may even predate the Earth itself, arriving on icy comets that bombarded the young planet and helped fill its oceans. To think of a raindrop in this way is to see it not just as fleeting moisture, but as a traveller across deep time. The global water cycle is both relentless and delicate. It is relentless because it never stops moving water between sky, land and sea without pause. It is delicate because small shifts in temperature, air currents or chemistry can alter its rhythm, changing where rain falls and where drought lingers. For life on Earth, the cycle is not simply background, it is the foundation. Crops depend on predictable rainfall. Rivers carve landscapes, oceans circulate heat, and through it all the chemistry of water molecules binds the cycle together. Rain is the visible signature of this grand process, the moment when the sky gives back what it borrowed. In each falling drop is the essence of a journey that spans continents, oceans and ages. It is chemistry in motion, carrying not only the freshness of the present, but also whispers of the past. To watch rainfall is to glimpse the ancient pulse of the planet, the endless recycling of molecules that have seen ages come and go, yet still find their way back to Earth, drop by drop. The rain we experience today nourishes crops, washes the air and fills rivers. But long ago it may have done something even more remarkable. It may have helped spark life itself. Billions of years in the past, when the young Earth was a restless and stormy world, rain fell not onto fields and forests, but onto bare rock and steaming volcanic plains. Into these early pools and puddles, raindrops may have delivered the raw ingredients that eventually built living cells. To see rain in this light is to see it not only as weather, but as one of the planet's oldest chemists. One idea is that rain brought essential molecules from the sky to the ground, concentrating them in small places where they could interact. In the early atmosphere, conditions were very different from those today. The air was thick with gases like methane, ammonia, hydrogen and water vapour. Volcanoes added carbon dioxide and sulfur compounds. Without the stabilizing influence of plants or an oxygen-rich atmosphere, storms were frequent and violent. Lightning forked through the skies constantly, splitting molecules apart and allowing them to recombine in novel ways. When rain fell, it swept these new products down into pools and puddles, gathering them into liquid laboratories on the Earth's surface. Scientists have long wondered how simple molecules could have arranged themselves into the complex structures of life. One influential experiment in the 1950s provided a clue. Two researchers, Stanley Miller and Harold Urey, recreated what they believed the early Earth's atmosphere might have been like. They filled a closed system with methane, ammonia, hydrogen and water vapour, then zapped it repeatedly with electrical sparks to mimic lightning. After a week, the water at the bottom of their apparatus had turned brown. When analysed, it contained amino acids, the fundamental building blocks of proteins. The implication was astonishing. Lightning and rain working together in the right atmosphere could spontaneously create the ingredients of life. The experiment was not a complete recipe for life, but it demonstrated an important principle. Energy from lightning and chemistry from rainfall could generate complexity out of simplicity. Once deposited into ponds and pools, these amino acids and other organic molecules might have accumulated further, forming rich chemical soups. In shallow waters, where evaporation could concentrate them even more, they might have linked together into chains, laying the groundwork for proteins, nucleic acids, and eventually self-replicating systems. In this way, rain was not just a delivery system, but a concentrator and stage setter, making conditions ripe for further steps toward life. There are other reasons to think rain played a vital role. Water is an ideal medium for chemistry, allowing molecules to bump into one another, react and disperse. But water alone can also dilute things too much, spreading molecules so thin that reactions struggle to happen. Rain, by filling small pools and then drying partially under the sun, could have created cycles of concentration and dilution. These wet-dry cycles are thought to be crucial for forming long molecular chains like RNA or DNA. In essence, rain may have stirred the pot, drying and refilling primitive ponds until complexity began to emerge. Not all scientists agree on the exact details. Some suggest that life may have begun not in surface puddles, but deep at hydrothermal vents in the ocean. Others argue for icy environments or even delivery of organic molecules by comets. Yet even in these scenarios, rain still may have played a supporting role shaping the atmosphere and distributing materials across the planet. The beauty of the water cycle is that it connects everything from ocean to land to sky. Wherever the ingredients for life appeared, rain would have been one of the forces moving them into place. It is worth imagining what those first rains must have been like. The young Earth lacked the forests and fields we see today. Instead, rain fell onto bare rock, into volcanic craters, and across landscapes of shallow seas. Every storm may have been a chemical experiment mixing gases, minerals and energy into unpredictable results. The smell of those rains would not have been the comforting peatry we know, but likely sharp and acrid with sulfur and ammonia. Yet, within that alien atmosphere, droplets were carrying the seeds of something entirely new. This perspective even extends beyond our own world. Could alien planets also experience rain chemistry? On Titan, Saturn's largest moon, rain falls not as water, but as liquid methane. While this does not support life as we know it, it shows that rain is a universal process wherever an atmosphere and liquid coexist. On Venus, droplets of sulfuric acid fall through the thick clouds, though they evaporate before reaching the surface. On distant exoplanets, astronomers believe it might even rain molten iron, glass, or exotic hydrocarbons. If rain on Earth helped build life, it is tempting to wonder whether rains on other worlds might play similar creative roles, albeit with very different ingredients. The story of rain and life's beginnings is not one of certainty, but of possibility. Each drop falling onto the young planet carried with it gases from the sky, minerals from volcanic eruptions, and the electrical energy of storms. Together, these contributions may have nudged chemistry toward biology, from molecules toward metabolism, from chance reactions toward the first fragile cells. Life did not appear in an instant. It was coaxed into being by countless interactions, many of them happening in water delivered from the clouds above. To think of rain in this way is to give it a new kind of significance. Today, it fills rivers, nourishes plants, and cleans the air. But in the deep past, it may have been one of the midwives of life itself. Each falling drop was a tiny experiment, a carrier of possibility, an agent of transformation. When you feel rain on your skin, you're touching not just water, but a reminder of those ancient days when the first whispers of life might have been written into puddles by storm and sky. When rain falls on a field, a forest, or even a potted plant on a windowsill, it is easy to think of it as simple hydration. Water in, plants grow, end of story. But in truth, every shower is a kind of chemical conversation between sky and soil, droplets and leaves. Rain brings with it more than moisture. It carries dissolved gases, nutrients, and even signals that plants interpret in surprising ways. To watch a garden brighten after rain is to witness a dialogue that has been unfolding since the first green shoots colonized the land. One of the most important chemical gifts rain provides is nitrogen in a usable form. The atmosphere is rich with nitrogen gas, but it's locked away as N2, a molecule so stable that plants cannot break it apart themselves. Rainstorms, particularly those accompanied by lightning, perform the difficult work of splitting nitrogen atoms and binding them with oxygen to form nitrates. These nitrates dissolve into raindrops and descend to the earth where they sink into the soil. For plants, nitrates are gold, the raw material for amino acids, proteins, and nucleic acids. Every leaf, stem, and seed relies on nitrogen, and rainfall is one of the quiet couriers delivering it. Alongside nitrogen, rain also carries dissolved carbon dioxide. As droplets fall through the air, they absorb CO2, forming a weak solution of carbonic acid. Though mild, this dissolved gas enriches the soil with carbonates that plants and microbes can use. In some cases, carbon dioxide in raindrops also plays a role in buffering soil chemistry, helping to balance acidity and keep nutrient cycles steady. Even oxygen present in the atmosphere finds its way into rainfall. As raindrops splash onto soil and seep downward, they carry with them small amounts of dissolved oxygen, helping to aerate the upper layers of earth where roots spread. The direct benefits of rain to plant health extend beyond the nutrients and droplets. Rain washes leaves, clearing them of dust, pollen, and pollutants that accumulate over dry spells. A plant's leaves are its solar panels, converting light into energy through photosynthesis. Dust on their surfaces can reduce efficiency, shading them from sunlight and clogging the tiny pores called stomata. A good rain is like a thorough cleaning service, restoring leaves to their full working order. Afterward, the canopy often looks brighter, the green more vivid, not only because of the water shine, but because the leaves are newly polished for their work. Rain also influences the balance of moisture in the soil. Roots depend on a delicate ratio of water and air in the spaces between soil particles. Too little water and roots struggle to absorb nutrients. Too much and oxygen is pushed out, suffocating them. Gentle rains are particularly effective at soaking into the ground, replenishing water without overwhelming root systems. Heavy downpours can be less ideal, sometimes compacting soils or causing runoff that carries nutrients away. Yet even then, the cycle is reset, and life continues its negotiation between abundance and scarcity. Plants are far from passive in this relationship. They have evolved ways to respond chemically to rainfall. Some species release hormones that trigger rapid growth after soaking. Desert plants, for example, may remain dormant for months, then burst into bloom following a rainstorm, responding to the sudden availability of water and nutrients. In agricultural settings, farmers sometimes notice crops visibly perk up within hours of rain, not just because of water, but because of this internal chemistry of response. Seeds, too, can be attuned to rain. The earthy fragrance we call petrichor is partly produced by oils secreted by plants during dry spells. These oils accumulate in soil and rock, lying dormant until rain releases them into the air. But petrichor is not merely a perfume for humans to enjoy. It may act as a chemical signal to seeds waiting in the soil. For some species, these compounds announce that rain has arrived and conditions are finally right for germination. Seeds that might otherwise remain dormant for years can sense the shift and awaken, sprouting into new life. In this way, rain carries a chemical message across generations of plants. Now is the time to grow. There is a subtle choreography in the way plants respond to moisture at their leaves and roots. Stomata, the tiny openings on leaf surfaces, often close during dry weather to conserve water. When rain arrives and soils are replenished, plants can afford to open them wider. This not only allows carbon dioxide to flood in for photosynthesis, but also permits transpiration, the release of water vapour which cools the leaf. A fresh rain thus resets the balance, allowing the plant to breathe more freely. Rain's chemical conversation with plants even affects the wider environment. When rain delivers nitrates and other nutrients, plants grow more vigorously, producing more leaves and stems that in turn release oxygen into the atmosphere. Healthier plants support herbivores, which support carnivores, rippling through entire ecosystems. The chemistry of a single shower can cascade outward, influencing the rhythm of a forest or the productivity of a meadow. Human agriculture has long depended on this interplay. Before synthetic fertilizers were invented, farmers relied heavily on the natural fertilization provided by rain. Even today, rainwater often contains a more balanced mixture of nutrients and fewer salts than irrigation water, making it particularly beneficial for crops. Gardeners often remark that plants look greener and healthier after a rain compared to artificial watering, and science supports this observation. The combination of dissolved gases, nitrates, and the physical washing effect makes rainwater unique. It is easy to think of rain as simple hydration, but for plants, it is more akin to a full conversation, one that involves nutrients, cleaning, hormonal responses, and even signals for seeds to awaken. Every drop that falls onto a leaf or seeps into the soil is carrying more than moisture. It is carrying information and sustenance, messages written in the language of chemistry. The next time rain freshens a garden or forest, consider the quiet dialogue taking place. Nitrogen forged by lightning is slipping into roots, dust is being rinsed from leaves, seeds beneath the soil are sensing chemical cues that tell them to stir. Rain may seem like an ordinary part of weather, but for plants, it is a partner, a messenger, and a catalyst, engaging them in a conversation that has continued for hundreds of millions of years. When rain falls over the ocean, it enters a world already dominated by water. At first glance, it may seem like a small and redundant act, adding fresh droplets to an endless salty expanse. Yet, the chemistry of those raindrops matters more than it might appear. They create subtle but important changes at the ocean surface, influencing salinity, nutrient mixing, and even the behavior of microscopic life. Far from being irrelevant, rain is a chemical mediator, linking atmosphere and sea in a constant dialogue that keeps marine systems alive and dynamic. The ocean is salty because of the minerals carried into it by rivers over millions of years. Sodium and chloride are the most abundant, but magnesium, calcium, potassium, and sulfate also contribute to its chemistry. On average, seawater contains about 35 g of dissolved salts per litre, a balance that marine life has adapted to with exquisite precision. Rainwater, by contrast, is fresh. When it falls onto the ocean, it creates a temporary layer of lower salinity at the surface. This dilution is often only a few km thick, but for the organisms that live in the delicate boundary between air and sea, it can make all the difference. This surface layer is called a lens of freshened water. It floats because fresh water is less dense than salt water, and it can persist for hours or even days depending on winds and currents. The sudden reduction in salinity affects the way gases exchange between ocean and atmosphere. For instance, a freshened surface can change how easily carbon dioxide dissolves into the sea, or how oxygen moves out. Rain is therefore not just watering the ocean, but actively altering the chemical interface through which gases pass. Raindrops also deliver their own chemical passengers. As they fall, they collect gases such as carbon dioxide, nitrogen oxides, and sulfur compounds from the atmosphere. They may also carry tiny particles of dust, pollen, or sea salt that seeded their formation. When these drops meet the sea, they deliver this cargo to the surface waters. Some of these additions are pollutants, but many are nutrients. Dust particles rich in iron, for example, are known to stimulate plankton blooms in parts of the ocean that are otherwise nutrient poor. Rain becomes a vehicle, transferring elements from the land and sky into the sea's chemical machinery. The impact of rain is especially noticeable in tropical oceans where sudden downpours are common. After heavy rainfall, the surface waters become stratified with a fresh layer on top and saltier water below. This layering reduces mixing, temporarily isolating the surface from the deeper ocean. While this might seem restrictive, it actually creates unique opportunities for plankton near the surface. The fresh layer stabilizes their environment, keeping them in well-lit shallows where photosynthesis is most efficient. When nutrients are present, these conditions can encourage rapid blooms, fueling the base of the food web. In other cases, rain can help stir nutrients upward. Strong storms not only freshen the surface, but also agitate the ocean with wind and waves, breaking down stratification and mixing deep, nutrient-rich waters into the upper layers. The combination of rainwater dilution and mechanical mixing creates a chemical reset, redistributing essential elements like nitrogen, phosphorus, and iron to the organisms that need them. Plankton blooms often follow such storms, sometimes visible from space as vast green or turquoise swirls across the sea. The chemistry of rain itself varies depending on where it falls. Rain over the open ocean is relatively clean, carrying mainly sea salt and dissolved gases. But near coasts or industrial regions, raindrops may contain higher concentrations of pollutants such as sulfur and nitrogen oxides, which can contribute to ocean acidification. While individual drops are small, their cumulative effect is significant, especially in enclosed seas or estuaries where dilution is slower. In this sense, rain reflects not only natural processes, but also human influence, serving as a delivery system for both nutrients and contaminants. Plankton, the tiny drifters that form the foundation of marine ecosystems, are particularly sensitive to rain's chemistry. Some species thrive in the slightly diluted surface waters that follow a downpour, while others are stressed by sudden changes in salinity. Phytoplankton, the plant-like microbes that photosynthesize, respond quickly to the influx of nutrients delivered by rain. Their growth, in turn, supports zooplankton, small fish, and eventually the entire marine food chain. Thus, a rainstorm over the sea can trigger ripples of productivity that extend far beyond the surface. For marine animals that breathe air, such as dolphins or seabirds, the freshened surface provides no direct hydration. They still rely on food and metabolism for water, but the indirect effects are profound. By shaping plankton populations, rain influences fish stocks, and ultimately the health of larger predators. Fishermen in some regions even note seasonal patterns, with certain rains heralding productive fishing grounds, a cultural observation rooted in real ocean chemistry. There is also a poetic side to rain at sea. Sailors throughout history have welcomed rainwater as drinkable, in stark contrast to the salty ocean surrounding them. In a lifeboat or on a long voyage, a shower could mean survival. Even now, rain is collected on ships and islands for freshwater supply. This duality, fresh from above, salt from below, is part of what makes the rain-ocean relationship so striking. It is a meeting of two waters, one ancient and mineral-rich, the other new and transient, combining in layers and exchanges. From a planetary perspective, rain over oceans is part of a grand balancing act. It links the water cycle of evaporation and condensation with the biogeochemical cycles of nutrients. Oceans lose water constantly to evaporation-feeding clouds. Those clouds give it back in the form of rain laced with atmospheric chemistry. This constant exchange keeps the sea not only full, but also chemically active, adjusting salinity, redistributing minerals, and fueling life. Raindrops then are far more than anonymous beads of water falling into an endless sea. They're couriers between sky and ocean carrying dissolved gases, minerals, and nutrients. They alter salinity, stir layers, and spark life in the tiniest organisms whose growth resonates throughout entire ecosystems. To see a rain shower over the waves is to witness a chemical handshake between atmosphere and ocean, one that has been repeated for billions of years and will continue as long as clouds drift above the sea. Rain has always held a place of fascination in human history. Long before meteorology or chemistry could explain it, people turned to myth and ritual to make sense of water falling from the sky. To live by farming or hearing was to depend on it, and to endure drought was to risk famine. Rain was never just weather, it was blessing, curse, mystery, and sometimes even divinity itself. From ancient myths to modern science, the story of rain is deeply intertwined with the story of humanity. In many early cultures, rain was imagined as a gift from gods or spirits. The Greeks believed in Zeus, the sky father whose thunderbolts commanded storms and whose moods determined whether crops flourished. In Mesopotamia, the storm god, Adad, also known as Ishka, was thought to control the rains that kept fields fertile along the Tigris and Euphrates. In Hindu tradition, Indra wielded his thunderbolt to release life-giving rain, a symbol of both power and sustenance. These beliefs reflected not only reverence for the heavens, but also the undeniable chemistry of survival. Without water, seeds could not grow, and without growth, there was no life. Rituals to invite rain were common across the world. In parts of North America, Native American tribes developed elaborate rain dances passed down through generations. These were not mere superstitions, but deeply symbolic practices often performed with music, costumes, and community participation. The dances acknowledged the dependence of humans on natural cycles, and sought harmony with forces beyond human control. In Africa, sacred ceremonies were performed during droughts with offerings and chants designed to persuade the sky to open. Across Asia and South America, similar traditions flourished, each blending cultural meaning with a practical wish: water for crops, herds, and people. In many of these rituals, one can see the earliest recognition of rain's chemical duality. People may not have described it in terms of molecules or atmospheric reactions, but they sensed that rain was not random. It carried fertility, changed the taste of soil, and affected the health of plants. Some even connected rain with lightning, intuitively recognizing a link between storms and soil fertility. What they lacked in scientific language, they expressed in myth and dance. As societies grew more complex, the blessings and dangers of rain became clearer. In agricultural civilizations, seasonal rains were both eagerly awaited and feared. The monsoon in South Asia, for example, remains a dramatic example of this duality. A timely monsoon brings bumper harvests and prosperity, but a delayed or failed monsoon brings drought and hunger. Conversely, a monsoon that arrives with too much force can flood fields, wash away villages, and ruin crops. In this way, rain was a double-edged sword, essential for survival, yet capable of destruction. Ancient records from China's dynasties, Egypt's kingdoms, and Mayan city-states all describe cycles of prosperity and hardship tied directly to rainfall. The Industrial Revolution added a new chapter to humanity's relationship with rain. As factories multiplied and cold smoke filled the air, people began to notice changes not only in the quality of air but also in the nature of rain itself. It was in the mid-19th century that the term acid rain was first coined by chemist Robert Angus Smith, who observed that rainfall in industrial regions was unusually corrosive. The culprit was sulfur dioxide and nitrogen oxides from burning fossil fuels, which dissolved in raindrops to create acids stronger than the natural carbonic acid found in normal rain. The consequences were visible and troubling. Buildings and statues blackened and eroded. Forests weakened as acid leached nutrients from soils. Lakes lost their fish populations as acidity rose beyond what aquatic life could tolerate. Acid rain was a revelation of sorts, a reminder that rainfall was not an isolated event, but a mirror of the atmosphere it passed through. Humanity had altered the chemistry of the skies, and rain was carrying the evidence down to Earth. This growing awareness helped spark the modern environmental movement. By the late 20th century, international agreements such as the Clean Air Act in the United States and CROSPER treaties in Europe began to curb emissions. Sulfur scrubbers in smokestacks and catalytic converters in cars reduced the pollutants that produced acid rain. Over time, rainfall in many regions became less acidic. Lakes and forests began to recover, and acid rain became one of the first major global environmental crises to show signs of improvement after intervention. The history of acid rain stands as both a warning and a success story. Human activity can damage the chemistry of rain, but collective action can also repair it. Beyond industry, rain has continued to play a central role in agriculture. For farmers, the timing and quality of rain is as critical now as it was thousands of years ago. Too little, and crops fail. Too much, and fields flood. The arrival of rain at the right time can mean abundance. Its absence can mean famine. Agricultural calendars have been built around the expectation of rain for centuries. And irrigation systems were some of humanity's earliest technologies to manage water when the skies could not be trusted. Even today, satellites and weather models are used to predict rainfall with entire economies, depending on accurate forecasts. Yet, despite all our progress, rain still inspires awe. Even with satellites tracking storm systems and models predicting rainfall patterns, people still step outside and marvel at the smell of the first drops hitting dry earth, the coolness of a sudden shower or the arc of a rainbow after a storm. Rituals may have changed, but the reverence remains. Rain reminds us of our dependence on natural cycles and our vulnerability to forces beyond our complete control. In many ways, human history is written in water. Civilizations have risen where rains were reliable and faltered where they failed. Myths and rituals turned raindrops into sacred gifts. Industrial smog turned them into acid warnings. Farmers continue to watch the skies with the same mixture of hope and worry that their ancestors felt thousands of years ago. Rain has been divine, destructive, and deeply practical all at once, Each drop falling from the sky today carries echoes of that long history. It is not only part of the natural water cycle, but also part of our cultural and scientific story. Rain gave us myths of gods, inspired dances and rituals, forced us to reckon with industrial pollution, and continues to sustain agriculture. It is weather, chemistry, and history woven into every drop that touches the ground. To walk in the rain is to share an experience with ancestors stretching back to the dawn of agriculture, each generation looking up, wondering, and depending on the same falling water. Rain is often thought of as a symbol of cleanliness, rinsing the world and leaving behind a sense of freshness. Yet in the modern era, raindrops are not always pristine. As they fall through the air, they collect whatever is present in the atmosphere and in cities and industrial regions that can mean a cocktail of pollutants. The chemistry of rain has become a mirror of human activity, reflecting the engines we run, the fuels we burn, and the air we breathe. Urban smog is one of the biggest influences on modern rainfall chemistry. In cities where cars, factories, and power plants release exhaust into the air, clouds form in an atmosphere heavy with nitrogen oxides, sulfur compounds, volatile organic molecules, and fine particulate. Raindrops condensing in such environments trap these substances, delivering them to the ground in every shower. The effect is not subtle. Measurements show that rain falling in heavily polluted urban areas can contain significantly higher levels of acidity and chemical contaminants compared to rainfall over rural or oceanic regions. One particularly striking example of this phenomenon is brown rain. In areas with high levels of soot or dust, raindrops can become visibly discoloured, carrying down suspended particles that stain surfaces and leave behind dirty residues. During the height of industrial coal burning, such rain was common, blackening clothes, stonework, and even skin. Even in more recent decades, episodes of brown or yellowish rain have been recorded when industrial smog or desert dust was swept into storm systems. These unusual rains remind us that droplets are not just water, but also collectors of whatever floats in the air. Soot-laden precipitation is more than an inconvenience for clean laundry or polished cars. When deposited on soils, waterways, or snowpacks, it can alter ecosystems. Dark particles settling on snow reduce its reflectivity, causing it to melt more quickly under sunlight. In streams and lakes, pollutants carried by rain can stress aquatic life. On soils, acidic rainfall can leach essential minerals while adding toxic compounds. The journey of a raindrop through polluted skies changes its chemistry in ways that ripple through the environment. Climate change adds further complexity to the chemistry of rain. As global temperatures rise, patterns of evaporation, cloud formation, and precipitation are shifting. Warmer air can hold more water vapor, leading to heavier downpours in some regions and drought in others. These shifts alter how pollutants are distributed in rainfall. In addition, increased wildfires release vast amounts of soot and organic aerosols into the atmosphere, which become nuclei for cloud droplets. Rain falling through smoke-laden skies carries chemical signatures of those fires. From carbon compounds to trace metals, even natural rain is no longer entirely free of human influence. As industrial activity and climate change reshape atmospheric chemistry on a global scale, aerosols, tiny particles suspended in the air, play a crucial role in this story. They act as seeds around which raindrops form, but they also determine the chemistry of the resulting precipitation. In clean air, natural aerosols like sea salt or dust dominate, producing rain with relatively simple chemical profiles. In polluted air, aerosols may include sulfates, nitrates, black carbon, and industrial residues, leading to raindrops with far more complex chemistries. Scientists studying rainfall today can often trace pollutants back to their sources by analysing the chemical fingerprints left in the water. Each storm becomes a record of human activity etched into its droplets. Despite the challenges, there are reasons for optimism. In many countries, air quality regulations have led to measurable improvements in rain chemistry. The Clean Air Acts in the United States and similar measures in Europe significantly reduced sulfur dioxide and nitrogen oxide emissions in the late 20th century. As a result, rain in those regions has become less acidic, lakes have recovered, and forests have regained vitality. In places where air quality is improved, so is the purity of rainfall, proving that human intervention can change the course of atmospheric chemistry for the better. The progress highlights an important truth. Rain is not just a passive background event. It is a conveyor belt taking whatever we release into the air and delivering it back to the Earth. Cleaner skies mean cleaner rain, and cleaner rain means healthier ecosystems. The link is direct and undeniable. Every improvement in emission controls, every reduction in pollutants echoes in the chemistry of the next shower. Yet the work is ongoing in rapidly industrializing regions. Acid rain and polluted precipitation remain significant problems. Urbanization continues to add nitrogen oxides and particulate matter to the air. Agricultural practices contribute ammonia and other compounds that alter rainfall chemistry in rural areas. The global picture is uneven, with progress in some regions and setbacks in others. Rain, as always, reflects these realities with perfect honesty. There is something humbling about this. The rain that falls on our heads or splashes into our rivers is a report card from the sky, showing us how we are treating the atmosphere above. It can be as pure and refreshing as the air over a forest, or as stained and acrid as the air over a factory. The difference lies in choices made about energy, industry, and the stewardship of air. And yet even polluted rain carries with it the same timeless role, a link between earth and sky, a mover of water, a reminder of cycles larger than ourselves. Each drop still falls under gravity's pull, still nourishes soils and rivers, still participates in the grand circulation of water that has shaped the planet since its beginning. The chemistry of those drops may change with human influence, but their presence reminds us that we are part of a system far older and larger than our industries. Rain in all its forms remains both teacher and mirror. It teaches us about chemistry, cycles, and resilience. It mirrors our actions, clean or dirty, hopeful or harmful. To work toward a purer rain is not merely an environmental goal, but a way of aligning ourselves with the natural rhythms that sustain life. After all, every drop that falls from the sky eventually finds its way into the water we drink, the soil that feeds us, and the air we breathe. In that sense, polluted or clean, the rain is not distant. It is a reflection of us falling back upon us drop by drop. Rain is not the only way water falls from the sky. When temperatures dip low enough, clouds begin to craft crystals, pellets, and icy coatings, transforming liquid precipitation into solid forms. Snow, hail, and freezing rain are all born from the same molecular building block, water. Yet they take on dramatically different shapes and behaviors because of subtle changes in chemistry and physics. These frozen forms of rain reveal just how versatile water can be, how its simple structure leads to endless variety in the skies. Consider hail, which begins its life as a supercooled droplet. Supercooled water is liquid that has been chilled below the normal freezing point of 0 degrees C, yet refuses to solidify because it lacks a surface to crystallize upon. In the turbulent environment of a thunderstorm cloud, these supercooled droplets collide with small particles such as dust or even embryonic ice crystals. The collision provides the needed surface for freezing, and the droplet instantly hardens into ice. Once a small lump of ice forms, the real drama begins. Powerful updrafts inside thunderstorm clouds toss it upward, where it meets more supercooled water. Each encounter adds another layer of ice, like a pearl forming its concentric shells. The stronger the updraft, the longer the hailstone can stay aloft, collecting layer upon layer. When the stone grows too heavy for the storm to support, it falls to the ground, sometimes as small pellets, sometimes as golf ball-sized or larger missiles of ice. Cross-sections of hailstones often reveal these layers like the rings of a tree, chronicling their journeys up and down through the storm. Snow, in contrast, forms more gently. At its heart lies the unique geometry of water molecules. Each water molecule consists of 2 hydrogen atoms bonded to 1 oxygen atom, creating a bent shape with slight positive and negative charges. When water freezes, these charges encourage the molecules to lock together in a hexagonal pattern. This geometry is why snowflakes nearly always exhibit 6-sided symmetry. As a crystal grows within a cold cloud, water vapor condenses onto it, extending branches outward. Tiny changes in temperature and humidity along the way influence the exact form, producing an astonishing diversity of shapes. Some snowflakes resemble delicate stars, others needles or plates, but all obey the same hexagonal blueprint. The chemistry of snow is also distinct from that of rain. As snowflakes fall, they trap pockets of air, dust, and sometimes even atmospheric pollutants. Each crystal is like a tiny time capsule, recording the